So red flushes them out, and I go boom, 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 boom.
Feathers everywhere.
No, I missed all three.
Oh.
You should have seen Red, though. He gave me that sad dog look like I was a skunk, just give him a snootful.
Dog's honest.
Yeah, you can't blame him on that. Never seen another bird all day.
Phew. How about some coffee?
Yeah, sure. That's great. You know, Al, I've been meaning to talk to you about something.
If it's shooting help you need, you see a gun club.
No, it's not that. It's electricity.
Electricity?
Yeah, I can deal with the plumbing part of the job.
Yeah, well, of course you can. You're smart.
But all that electrical stuff just doesn't make sense.
No harder than plumbing.
No, I just can't get it, though.
Let me ask you something. Has anybody ever taken the time to explain to you the basics of electricity, step by step?
You know how it is, Al. Nobody has any time.
We don't have to be back on the job for a couple hours. Why don't you come down to the basement and let me show you some basic things about electricity?
I don't want to impose on you.
You're not
though.
imposing. I promise. I'm glad to do it.
Okay.
All right?
Yeah.
Drink up. Come on.
Welcome to Weil McLain's Hydronic Education and Training Program, Basic Electricity for the Heating Professional. This program was developed to help the heating professional become more comfortable with the electrical part of an installation or service call. Many heating professionals are unsure of electrical terminology, what electrical tools and test equipment to use, how to read wiring diagrams, and how electrical components are wired. Weil McLain has provided this training program to help take the mystery out of the electrical portion of the heating installation. Here's how this program works. We'll talk about the basics of electricity, electrical parts and supplies, tools, electrical components, wiring diagrams, completing simple electrical connections, and troubleshooting an electric circuit in a heating system. Then, at regular intervals, we'll ask you to stop the videotape and complete the section review in your workbook. Remember, you can rewind and review the video segments at any time.
Let's begin our discussion with a look at a basic electric circuit. A circuit starts at a source of power, typically a fuse or circuit breaker box. Here, two wires go from the power source to a light bulb. The top wire is black and the bottom wire is white. The black wire is referred to as the hot wire because it carries the electric power. The white wire is called the neutral wire and is used as a return line to complete the electric circuit. The standard color coding makes for easy identification and consistency in the wiring. This basic electric circuit is similar to a basic hot water piping arrangement. It begins with a source of water, such as a boiler. A supply pipe carries the hot water to a radiator, and a return pipe completes the piping circuit back to the boiler. What happens if we add a zone valve in our water circuit or a switch in the electric circuit? Well, a zone valve permits the flow of water or stops the flow of water, and an electric switch permits the flow of electricity or stops the flow of electricity. Both devices allow us to control the flow of power. An electric switch is normally connected in series to the hot or black wire. In order for this switch to work, you need to cut the black wire and attach it to the switch. This is similar to installing a zone valve in this piping. On most electrical switches, the wiring connections are located on the same side. One wire on the top and one wire on the bottom. When a zone valve is open, water is allowed to flow through the piping circuit. When a zone valve is closed, the water cannot flow. However, with an electric switch, when the switch is open, the connection between the two wires is broken. Thus, the electricity cannot flow. and when the switch is closed, the connection between the two wires is made, allowing electricity to flow through the circuit. Remember, when dealing with electrical switches, the terminology is opposite from plumbing terminology. In electricity, a closed switch means there is a flow of electricity, and an open switch means there is no flow of electricity. Besides the black hot wire and the white neutral wire, you will usually find a bare copper or green insulated wire in a typical modern electric wiring circuit. This wire is called the ground wire. Its purpose is for safety. In our basic electric wiring circuit, the white neutral wire provides the return path that completes the circuit. The ground wire provides an additional return path for this electric circuit. The ground wire is provided in case the hot wire is accidentally broken or becomes exposed and touches something that is capable of conducting electricity, such as a junction box, a switch, or a receptacle, creating a short circuit. Short circuits can be very dangerous situations. If, for example, an electric switch becomes shorted and someone touches it, the electric current could attempt to complete the circuit through the person's body to ground. This is because the nature of electricity is to follow the path of least resistance to earth, called ground. This could be a person's body. The ground wire provides an easier path for completing the circuit. So if the electric switch is properly grounded and a short occurs, the switch ground wire becomes the path of least resistance rather than a person who might touch the switch. With all of this in mind, let's look at providing power to a typical boiler from the service switch. The same principles apply as with our basic electric circuit. The black hot wire from the circuit and the black wire from the boiler are attached to the switch. And the white neutral wire from the boiler is attached to the white wire of the circuit using a wire nut. The ground wire is grounded to the grounding screw on the service switch or metal J box. And that's all there is to it.
This section discussed a basic electric circuit, how electrical wires have a specific color coding, where typically the black wire is hot, how electricity flows through a circuit, how an electric switch operates, where on is a closed circuit and off is an open circuit. We also discussed electrical ground and how electricity always seeks to travel to ground, whether it's through a grounded electrical path or a person. Short circuits, and how an electric circuit is similar to a water piping circuit. In the next section, we will begin to define some basic electrical terms and applications. Turn the videotape off now and complete Section A in your workbook.
That's the trouble, Al. Ohms, watts, amperage, resistance, electrons, ground. It's all foreign language to me.
Well, what about valves and pressure and pipe diameter and BTUs?
Oh, that's good old English to me. Why, I know all that.
Yeah, but that's because somebody took the time to explain it all to you. You see, my daddy always said there's a word for everything, and once you know the meaning of that word, you got it.
I'm not getting this, Al.
You worry too much. Look, let's do this. Let's start with the basics, okay? We're talking volts, current, resistance. Okay.
Volt, amp, ohm, and watt are basic electrical units of measurement that all have a special relationship to each other. This section will explore these terms and their relationship through the use of two electrical equations, Ohm's law and Watt's law. We will also define series, parallel, and series parallel circuits. In order to truly understand electric circuits, you must first understand the terms voltage, current, resistance, and power, and their relationship to each other. These electrical terms are similar to the plumbing terms pressure, water flow, pipe size, and BTU, as we'll see later.
Voltage, current, and resistance are all electrical properties represented by symbols: E for voltage, I for current, and R for resistance. Voltage, E, is the force or electrical pressure that produces an electric current. Its unit of measure is the volt, V. Current, I, is the movement or flow of electrons. The measure of current is the ampere, usually referred to as amp, represented by the letter A. In order for current to flow in a circuit, there must be a complete path of the circuit back to the voltage source. Resistance, R, is the characteristic, like friction within a circuit, which opposes or resists current. A unit of resistance is the ohm, represented by the capital Greek letter, omega. The relationships of current, voltage, and resistance were first discovered by George Simon Ohm, a German physicist, in 1827. He performed a series of experiments which settled the questions of, 1, the way voltage is distributed throughout a circuit, and 2, the relationships of voltage, current, and resistance. What he discovered can be easily explained using water flowing through a pipe as an example. A given pipe size has a built-in resistance. A smaller pipe has more resistance than a larger pipe if the pressure is constant. If the pipe size remains constant and we increase the water pressure, the gallons per minute or the water flow rate will also increase. Thus, if we decrease the water pressure, the gallons per minute will decrease. If, on the other hand, our water pressure remains constant and we change to a bigger pipe, decreasing the resistance, then the gallons per minute will increase. Or if the pressure is constant and we decrease the pipe size, increasing our resistance, then the gallons per minute will decrease. This, in effect, is Ohm's law. Ohm's law states that the current in an electric circuit is directly proportional to the voltage and inversely proportional to the resistance. What does this mean? As voltage goes up, current goes up proportionally. And if the voltage goes down, the current goes down proportionally. In addition, for a given voltage, the current is inversely proportional to the resistance in the circuit. This means as the resistance goes up, the current goes down. Or as the resistance goes down, the current goes up. From Ohm's law, the amount of any one of the three properties of electricity, voltage, current, or resistance, may be calculated if the other two are known. Ohm's law is usually expressed by these three equations. E equals I times R. R equals E divided by I. I equals E divided by R. This graphic circle with the three symbols arranged in separate spaces can be used to figure the value of any one of the symbols. If, for example, we want to find the current I of a circuit, by placing a finger over the I, E divided by R remains. This tells us that current equals voltage divided by the resistance. Current, I, equals voltage, E, divided by resistance, R. This equation is shown as I equals E divided by R. To determine the current, I, using these common values, a voltage E of 120 volts applied to a resistance of 10 ohms, R. The equation shows us that 120 volts divided by 10 ohms equals 12 amps. To determine voltage, E, place a finger over the E on the circle, and I times R remains. To determine resistance, R, place a finger over the R, and E divided by I remains. There is one other important property of electricity that needs to be discussed. Power. Power is defined as the rate at which energy is expended, or as the rate of doing work. In electricity, the unit of measure of power is the watt. Power is the result of voltage pushing current through a circuit. If we add a water wheel to the end of the pipe with water flowing through it, we see that as the wheel turns, a certain amount of work is being accomplished. This work is the product of the water pressure at the wheel and the gallons per minute of water flowing through the pipe. If we increase the water pressure, then we increase the power. Or if we decrease the water pressure, then we decrease the amount of work or power. In electrical terms, the concept is similar. This is called Watt's law, and expressed by the equation known as pi, or P equals I times E, where P is electrical power, measured in watts. I is current, measured in amps. E is voltage, measured in volts. Increasing the voltage, pressure, or current flow through a circuit will increase the power, wattage. Or decreasing the voltage or current through the circuit will decrease the power, wattage. By using this circle representation for the power formula, any one of these three electrical properties, current, power, or voltage, can be found if the other two quantities are known. Say, for example, what is the power consumed? By covering the P, I times E remains. P equals I times E, or 10 amps, I times 110 volts, E, equals 1,100 watts. Since the watt is a small unit of power, we commonly use the kilowatt, which is equal to 1,000 watts. The abbreviation for kilowatts is kW. So the 1,100 watts is equivalent to 1.1 kilowatt. If a microwave oven consumes 600 watts of power and operates at 120 volts, how many amps of a 20 amp circuit will the appliance require? Again, using the circle and covering the symbol I, P divided by E remains. I equals P divided by E, or 600 watts, P divided by 120 volts, E, equals 5 amps, I. So I equals 5 amps. To determine voltage, cover the symbol E on the circle leaving P divided by I. E equals P divided by I. Or watts, P divided by amps, I, equals volts, E. These electrical properties, voltage, current, resistance, and power, and their relationship to each other, need a complete electric circuit in order to work. An electric circuit is a path, or a group of interconnected paths capable of carrying electric current. There are three basic types of circuits: the series circuit, the parallel circuit, and the series parallel circuit. The series circuit is a circuit supplying current to a number of devices connected in series. That is, the same amount of current passes through each device in completing its path back to the source of power. Almost everyone is familiar with a string of Christmas tree lights, where all the lights go out when only one of the lights burns out. These lights are connected in series. In completing its path back to the source of power, the current through light number 1 must also pass through lights 2, 3, and 4. It is apparent that if any one light burns out, the path for the current is no longer complete, and the other lights go out. A parallel circuit differs from the series circuit in that two or more devices can be connected directly to the same power source. Therefore, there is more than one path that the current can take to complete the circuit. If one device, for example a light, burns out, the other lights still have a complete circuit back to the power source and can still operate. Although many simple circuits are classified as being either a series or a parallel circuit, more complicated circuits are usually combinations of series and parallel circuits. These are called series parallel circuits. So you could have two devices in parallel with one another, and the parallel combination in series with another device, like a switch, and the source of power.
I have to admit, it's pretty clear in the way you put it, especially the circle.
Well, it's all very down to earth. Once you get past the fear of the unknown, it's very straightforward. It's like plumbing is very straightforward once you understand the basics.
I suppose.
Let's look at plumbing, okay? Voltage is like...
Water pressure.
Right.
Resistance is like the diameter of a pipe. And current is how much water flows through it.
Right. You learn fast, Dan.
And power is how much water or electricity is used to do some type of work. And a watt is a unit of power, right?
Right.
And circuits can be in series parallel or series parallel.
You've been paying attention, Dan. You're a fast learner.
I gotta learn this stuff, Al.
Sure makes the job a lot easier. How about a little quiz now?
Just so it isn't too tough.
I'm not going to ask you something you don't know.
All right.
Okay?
All right.
Okay. All right, now here goes. I'll be right back. My son thinks he is a rock star.
Yeah, he sounds pretty good.
Yeah. Quiz time.
Okay.
His amplifier puts out 180 extremely loud watts, and he uses every screaming one of them.
Yeah, no doubt.
And unbelievable as this may seem, he plugs that thing into an ordinary 120-volt circuit. How many amps does he draw?
Okay. Watts is P.
Mm-hmm.
120 volts is E.
Mm-hmm.
So that would be P divided by E equals I. In numbers, it would be 180 watts divided by 120 volts equals 1.5 amps.
Right. How many amps is he drawing now?
This section discussed basic electrical properties: voltage, current, resistance, and power, and their units of measurement, volt, amp, ohm, and watt. We also discussed how these electrical properties relate to each other using two simple equations. Ohm's law, where E equals R times I, and Watt's law, P equals I times E. Series, parallel, and series parallel circuits were also defined. Turn the videotape off now and complete Section B in your workbook. This section will discuss the electric power coming into your home, along with some electrical safety considerations. Before we begin, let's review some electrical basics. Remember, electricity flows in a circuit in much the same way as water flows in a plumbing application in a home. In order for electric current to flow through a circuit, it has to have pressure. Electric pressure is called voltage and is measured in volts. This pressure, voltage, forces current to flow along the black or hot wire in a circuit. Current is measured in amperes or amps. The current flows to a load, which is something that uses electricity like a light bulb or an electric motor. When current flows through a load, the electric power that is consumed is measured in watts. Finally, the current path from the load completes the circuit through the white or neutral wire.
Most homes have 3 power lines, 2 carrying 120 volts of electrical service, and the third is a grounded neutral wire. This power coming from the power company, when measured, could actually be in a range from 110 to 125 volts. For purposes of doing electrical calculations in this program, we will use a rating of 120 volts or 240 volts for the electric service. The electricity provided by the power company is called AC, alternating current. Typically, alternating current in the U.S. operates at 60 cycles per second. The other type of current that exists is direct current, DC. Here the current flows continuously in one direction from positive to negative. One of the most common sources of DC current is the battery.
So anyway, when the power comes from the street, it comes, instead of coming overhead, it comes underground, right to here, comes up through the meter, and into the distribution panel.
Distribution panel?
Distribution panel is a circuit breaker box or fuse box. Let me show you right around here to the right. Come on in the house.
All right.
The distribution panel. Now this one has circuit breakers.
Well, the one at my house uses fuses.
Yeah, they come both ways. Now the distribution panel serves 2 important functions. First, it distributes electric current throughout the house through branch circuits. Each one of the circuit breakers is a branch circuit.
So when a fuse blows at my house, that's why like some of the lights go out.
Exactly, which leads to the second important function. It prevents dangerously high electric current from going through any one branch circuit. Come on, let me show you something else.
When using a fuse for protection, the electric current for each circuit passes through a thin, heat-sensitive strip of metal in the fuse before it enters the circuit. If the circuit wires protected by the fuse are designed to carry no more than 20 amps of current, a 20-amp fuse is used. If more than 20 amps flows through the metal strip in the fuse, the additional current creates more heat in the thin metal protective strip circuit than it is able to handle. Thus, the strip melts, blowing the fuse, which opens the circuit. Electricity can no longer flow through the circuit. You can sometimes identify the cause of a blown fuse by just looking at the fuse. In this example, if the glass window is discolored by the melting of the metal strip, this usually means that there is a short somewhere within the circuit. A short means that the hot wire is touching something that conducts electricity in a direct path to ground with little or no resistance, like a metal box or an appliance. However, if there is little or no discoloration in the window and just the metal strip is melted in two, the circuit is probably overloaded. Today there are fuses designed to prevent you from using a fuse rated higher than what the circuit is rated for. These fuses, called S-type fuses, use an adapter that won't allow you to install the wrong size fuse. So you can't install a 20 amp fuse in a 15 amp fitting. Most distribution panels installed after 1965 use circuit breakers to protect the individual branch circuits. The circuit breaker has a permanent metal strip that as current flows through the strip, the heat from the current bends it. If too much current flows through the metal strip, the circuit becomes overloaded. The strip then bends enough to open the switch and stop the flow of electricity. This is called a tripped circuit breaker. Circuit breakers trip for the same reasons that fuses melt. Too much current caused by an overload, or there is a short somewhere in the circuit. Let's look at a typical residential distribution panel, one that uses circuit breakers. Power comes into the panel through two hot wires. Each wire delivers 120 volts. This is the supply current for the panel. There is also a third wire. This is called the neutral service wire. The two hot 120 volt wires are connected to the main breaker or fuse. This one is a circuit breaker, but it could be very large fuses. Main power fuses are usually cartridge type fuses. These come in many ratings and are usually installed as pullouts. This main breaker protects the panel and house wiring from receiving too much power. The main breaker has an on-off switch and is usually rated for 100 or 200 amps. Each side of the main circuit breaker is connected to a bus bar. These two hot bus bars each receive 120 volts of power for distribution to the independent branch circuits. The two bus bars are separated by plastic insulators to keep the 120 volt lines independent of each other. This circuit breaker is called a single pole 120 volt breaker, meaning it has only one hot line or voltage source, and it attaches to and draws current from only one bus bar. Single pole breakers are usually rated for 15 or 20 amps. The double pole 240 volt circuit breaker has two hot lines. This circuit breaker is connected to and draws current from both bus bars. The bus bars have a zipper tooth configuration, and the metal clips of the circuit breakers make the connection with the bus bar. Double pole circuit breakers are usually rated for 30 amps and supply power to high amperage appliances such as electric ranges, air conditioners, electric dryers, and so on. The neutral service wire is attached here to the ground neutral bus bar. This is where all neutral and ground wires from the individual branch circuits are also attached. All ground and neutral wires terminate at the ground neutral bus bar in the distribution panel. The distribution panel is also grounded to the ground neutral bus bar. This ground neutral bus bar is grounded to earth either by attaching to a metal water pipe inside the house or to a copper rod driven into the earth outside the house as close as possible to the meter. Many codes require grounding to a copper rod even if the system is grounded to a copper water main. Copper is used because it is such a good conductor. Be sure to check and follow the codes for your area.
So what you have to remember, Dan, is that electricity will always go to Earth.
Is that why they call it ground?
Ground or earth ground, yeah. Electricity will always seek to go to ground through the path of least resistance.
What's that have to do with home electrical circuits?
Well, it's extremely important to provide that path to ground in case your equipment develops a short. That ground wire provides a path of least resistance for the electricity to pass to Earth. If you didn't have that ground wire, that current might go through your equipment or worse, through a person.
It's one of the things that's always bothered me about working with electricity, Al. It's the possibility of getting shocked.
It's true, the potential for getting shocked is always there, but if you use your head, work only when you're well rested and alert, and use the proper methods, electrical wiring projects don't have to be that dangerous. You have to pay close attention. Maintain a healthy respect for the power you're controlling, and always take every precaution.
What kind of precautions, Al?
Come here. Okay, first thing you want to do is disconnect the power to the circuit you're working on. Either flip the breaker or take out the fuse.
What if I don't know what circuit's involved?
Then take out the main fuse, flip the main breaker.
So none of the circuits would be live then?
Exactly. Now, once you've done that, it's a good idea to put a note on the door. Let people know that you're doing some electrical work.
In case somebody comes to the panel.
Right, wants to turn the power back on. Hopefully they'll see the note and they won't turn the power back on.
That makes a lot of sense.
Yeah. Now, also, if it's possible, lock the box. That way you'll be sure nobody can turn the power back on.
You mean a padlock?
Yeah, a padlock's great. Come on.
Okay.
Never work with electricity in damp or wet conditions. And don't use tools, appliances, or electrical cords that are wet. Also, avoid touching anything metal when working with electricity, such as pipes, appliances, or faucets, because if you touched a hot circuit, you could become an easy path to ground, allowing the electrical current to flow through your body. Since there is a danger of fire or shock hazard through some failure of an electrical system, electrical codes have been written to provide approved materials and work standards. These electrical codes are similar to plumbing codes, such as BOCA's National Plumbing Code or the National Standard Plumbing Code. Most local electrical codes are based on the National Electrical Code, NEC. This code contains rules and regulations for the proper installation of electrical wiring and devices. The purpose of the National Electrical Code is to provide information considered necessary for the safeguarding of people and property against electrical hazards. Underwriters Laboratories, UL, was founded in 1884 and is a nationally recognized electrical testing laboratory. Most manufacturers of electrical equipment submit their electrical products to Underwriters Laboratories or other testing laboratories for testing to their safety standards. Products that pass UL testing and meet their safety standards are permitted to be labeled with a UL logo. When buying new electrical parts, look for the UL, Underwriters Laboratories, or CSA, Canadian Standards Association logo, or other testing laboratories labels on these parts. Use only parts with the same specifications as the part being replaced. If you are ever in doubt about the safety of any electrical repair, have it inspected by your local power company or a licensed electrician.
This section discussed the electric service coming from the power company into a home through the distribution panel and out into the home through branch circuits. It also discussed the importance of grounding and electrical safety issues. Turn the videotape off now and complete Section C in your workbook. This section will discuss electrical wire or conductors, how they're sized and graded, their rating for temperature and current capacity, along with the different types and common uses of electrical wires. We will also discuss proper methods to splice or connect wires, extend a circuit, and some of the more common electrical parts you may encounter.
A wire is an electric conductor. Wires for electrical applications are rated according to size. This rating is according to the American Gauge Standard, AWG. The diameter of the wire is expressed in whole numbers. The smaller the number, the larger the diameter of the wire. Wire may consist of a single strand, or it may consist of many strands wrapped together. Electrical wire is rated for ampacity, or the amount of current that can flow through the wire. This is determined by the wire size or number. According to the NEC, ampacity means the current in amperes a conductor can carry continuously under the condition of use without exceeding its temperature rating. In other words, if you were supplying power for 4 5-amp appliances, the wire must have a minimum rating of 20 amps.
And so wire is just like pipe. The bigger the diameter, the more current or water that can flow through it.
Well, with pipe, at least you know what you have by the diameter in inches. What's all that gauge stuff for?
You're making this difficult on yourself. How many shotguns you got?
I've got a 20 gauge for rabbit and a 12 gauge for ducks.
Which has a bigger diameter?
The 12 gauge, of course. Are you saying the same with wire?
The smaller the number, the bigger the size.
Why didn't I think of that?
And just as the smaller bore is used for smaller game, the bigger bore is used for bigger game.
And smaller wire is used for smaller electrical loads, and larger wire is used for larger electrical loads.
Yes, you got the basics. Terrific. Now we can get to the details. Look here.
Let's look at some typical applications for wires of different sizes. Remember, the larger the wire number, the smaller the wire size, and vice versa. The smaller the number, the larger the wire in diameter. Number 18 and number 16 wire is used for low voltage control circuits, typically 24 volts or less, such as doorbells, security systems, thermostats, and other low voltage heating components. Number 14 and number 12 wire are for normal residential wiring circuits, such as receptacle outlets or light fixtures. This is the gauge wire you would normally find in individual branch circuits in your home, such as for boilers and furnaces. Number 14 gauge wire is rated to handle up to 15 amps at 120 volts AC. Number 12 gauge wire is rated to handle up to 20 amps at 120 volts AC. Number 10, number 8, number 6, and number 4 wire is used for high voltage circuits, typically 240 volts AC. This wire is usually used for clothes dryers, ovens, ranges, cooktops, water heaters, heat pumps, central air conditioners, and feeders to sub-panels. Number 3, number 2, number 1, and larger wire is for main surface entrances and feeders to sub-panels. The National Electrical Code requires that all terminals and connectors be marked to show the type of wire that is allowed for use. A connector marked CO/ALR means that copper, aluminum, or copper-clad aluminum wires could be used. If a terminal is not marked with an AL or a CO/ALR, then only copper or copper-clad wire is acceptable for use. Typically for residential electric wiring, non-metallic sheathed Romex cable is used. This wire can range in size from number 14 to number 2 for copper wire and is available with 2 or 3 current carrying wires. These numbers stamped on the sheathing, 12-2 or 12-3, tells us that enclosed is number 12 gauge wire with either 2 or 3 conductors. The ground wire is never included in this number. 2-wire cable contains 1 black conductor, hot, 1 white conductor, neutral, and one green conductor or bare copper wire, which is ground. 3-wire cable contains an additional red hot wire. Flexible armored cable is sometimes called BX cable. This is insulated wire with a flexible metal covering. During installation, anti-short bushings are inserted at the end of BX cable to prevent the cutting of the wire insulation by the sharp metal armor. When adding a new general circuit, most codes today recommend number 12 gauge wire, which will handle 20 amps safely and can be protected by a 20 amp circuit breaker. This is due to the increased use of modern appliances such as TVs, hair dryers, microwaves, curling irons, and kitchen appliances. If you are extending an existing general household circuit, you'll probably find that it was installed using number 14 gauge wire. Number 14 gauge was once the general residential standard, and in some areas can still be used today. However, number 14 gauge is too thin to withstand the heat of 20 amps, and is rated for use up to 15 amps only. You can use number 12 gauge wire to extend a number 14 gauge circuit, keeping in mind that the circuit is still only rated to 15 amps due to the number 14 gauge cable. If you have questions about what gauge size wire to use for a particular job, check with your local code official. Always remember, any gauge wire too thin for its intended amperage is a fire hazard. Also, never use a fuse or breaker of a higher amp rating than that of the gauge of the wire in that circuit. Usually appliances like oil burners, boilers, water heaters, washers and dryers, and ranges are wired on their own circuit with the size of the wire dependent on the amount of electricity the appliance requires. Usually, these major 120-volt appliances will require number 12 or number 10 wire, while the 240-volt equipment will use either number 8 or number 6. Remember, new general residential circuits will usually be 120-volt, 20-amp, number 12 gauge lines. When planning a special 120-volt circuit, find the wattage or amperage for the equipment on the nameplate if listed. Then determine the required wiring for the circuit. The longer a circuit extends, the more voltage will be dissipated in overcoming the wire's resistance. When the circuit is excessively long, the voltage drop may be so great that an insufficient current reaches the appliance at the far end of the circuit. This could cause the appliance to run poorly or damage it. The answer in this case is to use a thicker gauged wire for longer circuits. The table in your workbook shows the maximum distances of a circuit as determined by the load in amps or watts. Some local codes require all interior electrical wiring to be run inside of electrical metallic tubing called thin wall conduit. This conduit is an additional safety device. Conduit can be bent by using a special tool called a hickey. If we needed to put a 90-degree bend in a piece of conduit, you first hook the hickey over the end of the conduit to the mark on the grip hook. Place a foot on the conduit and pull the handle back in the direction of the bend. Be sure to check the conduit occasionally to make sure you're getting the correct angle. Conduit requires the use of special connectors, couplings, brackets, and general hardware. This is a conduit set screw connector that you would use to attach the conduit to a metal box.
All right, good, excellent. All right, now give me the conduit there.
Make sure that once the conduit is attached to the box, that you tighten the set screw down to keep the conduit from pulling away from the box.
Just so it's nice and firm. So when you're splicing wires together, you need some kind of connector.
Like a wire nut.
Right. Wire nut is probably the most common type of connector.
What's that little spring thing inside there?
Well, that supplies the mechanical pressure that maintains the connection. The nut literally turns on the wire as if it were a bolt and then holds them firmly together. Now, to splice two wires together, first thing we need to do is to strip off a half, 3/4 of an inch of insulation. Okay? Then take a pair of needle nose or crimping pliers and twist these wires together.
You have to twist them clockwise.
Always have to twist them clockwise, yes, because a wire nut, just like any nut, goes on clockwise. And once you've got it on securely, make sure that there's no bare wire showing, okay? And then give each one of a tug to make sure that it's in there securely.
Seems nice and tight.
Good. Now, another type of connector is the solderless or crimp connector.
How does this work?
Let me show you. You insert the connector over the stripped end of the wire, and then using a pliers or the crimping end of the wire stripper, you squeeze it down tight. And then make sure again that it is nice and firm. Now, regardless of the connection method used, the NEC requires that all splice wires be housed in a plastic or metal box. And as you can see, these come in a variety of shapes and sizes.
Does that include a furnace or a boiler jacket?
Now, a furnace or boiler jacket is a protective box, sure.
Junction boxes are used where wire connections are made. These boxes are available in different depths depending on the number of connections that will be contained within the box. A chart in your workbook shows the maximum number of connections permitted by the NEC, according to the wire size and the box depth. When working with electrical boxes, junction or J boxes, you must punch out a knockout for each cable that will be entering the box. Use a screwdriver and, if needed, a hammer to do this. To secure the wire going into the box, use a Romex connector. Put the connector into the box and tighten the lock nut to the inside of the box. Feed the cable through the connector, making sure that you have enough cable, approximately 8 inches, to make your connection. Tighten down the 2 clamp screws. Give the cable a tug to make sure it is securely clamped. Then strip the cable sheathing back to where it enters the box.
This isn't going to be real tight on it also. So we're going to be a real good actress. Pretend it's real tight.
This section discussed electrical conductors, grading and size, rating for temperature and ampacity, types and common uses, splicing and connecting wires, insulation, including flexible armored cable and thin wall conduit, and common electrical materials. Turn the videotape off now and complete Section D in your workbook. This section will discuss electrical tools and electrical test equipment, along with their use in performing basic electrical work. You probably already have many of the tools needed to accomplish most simple electrical jobs, such as wiring a switch or receptacle. To accomplish either of these jobs, all you need is a screwdriver and needle nose or crimping pliers. Make sure that they have insulated handles, so that you're not physically touching any metal part of the tool. You should also add a multi-purpose wire stripping tool to your toolbox. This tool strips wire insulation, cuts wire, and makes crimps for connectors. You can also use this tool to measure the diameter of a wire. With these tools, simple electrical jobs are easy.
All right, let me show you how to wire a switch like this, Dan.
Okay.
All right, we're going to wire it right into a circuit. All right, now the first thing we want to do is
And turn off the power at the distribution panel.
Exactly. Now suppose we don't know which circuit or which fuse it is.
Okay, what do? You switch off the main circuit breaker or pull the main fuse.
Exactly. Very good. Now, got the wires already coming into the box. First thing we want to do is cut off about 8 inches of the sheathing. I've already cut off one. Okay. Pull it all the way back along with the paper. Just cut it off. All right. Then you match the wire gauge on the stripper to the wire you're using and strip back about 3/4 of an inch through each one of the wires, pulling it through the opening. Just stick it in there. Give it a little twist, pull. Works every time.
Looks pretty straightforward so far.
You got it. All right. Then you take the needle nose pliers and you form a little U at the end of the black wire, just like that. All right. And on the gold nuts on the end, hang one of the wires. Which way do you go?
Clockwise.
Clockwise. Always clockwise. As you tighten it down, it'll pull itself in tighter. Make sure it's secure. Make sure you don't have any insulation in behind the nut. All right. Do the same thing with the other one. All right. What am I doing? Okay. Excellent. All right. Okay.
What about the white wires?
White wires have to be joined together, so we take your needle nose pliers, twist them together. Always in a
clockwise
direction. And then once you have them twisted together, because you did them in a clockwise direction, wire nut will screw on securely.
And the ground wires?
The ground wires also have to be twisted together, but they also need to be grounded to the box.
How are you going to do that?
With a pigtail.
Pigtail?
Of course. Cut a little short piece of bare wire, twist the 3 together. All right. Clockwise, of course. All right. Wire nut them together. Voila!
Pigtail.
A pigtail.
Colorful terms in the electrical business.
No kidding. Now, the end of the pigtail, you make a loop, just like you did with the black wires, and you put it around the ground nut, the grounding screw in the bottom of the box.
Then you screw the grounding screw down.
And you screw it down. And you put it around which way?
Clockwise.
Clockwise. Always. Make sure they don't come off. You put it on clockwise, it tends to get tighter the tighter you tighten it. I use a little extra wire there and just clip off what I don't need in the box. Good. There you are. How's that?
Nothing to it.
Nothing to it at all.
If your switch uses push-in connections, use the strip gauge on the back of the switch to determine how much insulation to strip off the wire. Strip the wires. Insert the wires in the appropriately marked holes on the back of the switch. Attach ground wires together as just mentioned. If you have to remove a wire from a push-in connection, use a small screwdriver to push in on the marked release opening on the switch and pull the wire out at the same time. There are 2 other electrical tools you may want to add to your toolbox. A conduit bender, or hickey, is used in bending conduit to get around corners, or for the small offsets necessary at junction boxes. A fish tape is used to pull wire through conduit or other difficult places.
Now another item that's handy to have, Dan, is a continuity tester. It's used to check the metal pathways of a switch or other electrical component for continuity.
What do you mean by continuity, Al?
Well, continuity is the continuous path for the flow of current, like an unbroken circle. Now this continuity tester is just a flashlight with a couple of probes in the end, and when you contact the probes, you complete the circuit.
So you don't use it with the power on?
No, continuity tester has its own source of power, so we always use it with the power disconnected.
Can we use the continuity tester to check the switch we just wired?
Yeah, sure we can. Here, you hold the tester. Since there's no power, we'll connect this clip, and flick the switch a couple times.
When you turn the switch on, the light comes on. When you turn it off, it goes off.
That's because the switch is good.
Well, how do you know that?
Because when the switch is off, what happens to the path of electricity?
It's broken because the switch is open?
Exactly. And when the switch is on?
The switch is in a closed position, so the path of electricity is not interrupted.
Right. We have
Continuity.
All right. Now, what would you conclude if the switch was on and the continuity tester light didn't come on?
That would mean that the switch was bad or it was wired wrong.
You catch on quick.
A neon circuit tester is used to determine if voltage is present in a circuit and if the circuit is properly grounded. Basically, it is a small neon glow lamp with a pair of wire leads. By holding the insulated ends of the leads and touching the protruding metal contact tips on the hot and neutral wires, the light will glow if voltage is present. For example, to check an outlet for voltage and proper ground, first insert the tester leads into the hot and neutral slots of the outlet. If the circuit is hot, the light will glow. To check for ground on an outlet with a ground plug, insert one lead into the hot or narrow slot and the other into the ground U-shaped slot. The light will glow if the outlet is properly grounded. If the outlet has no ground slot, insert one lead into the hot slot and touch the other lead to the metal wall plate or the metal mounting screw. Again, if the light glows brightly, it is properly grounded. The volt-ohm meter, sometimes called a Vohm meter, is an electrical measuring instrument that you can use to check circuits, continuity, and to troubleshoot most electrical jobs. It will measure AC and DC voltages and resistance. Each meter comes with two leads, one red and one black. The red lead is positive and plugs into the red jack on the front of the meter. The black lead is negative or common and plugs into the black jack on the front of the meter. Notice on this meter that the top scale is for measuring ohms. You can test for resistance or continuity. The first thing you must do in performing an ohms test is to completely disconnect all the power from whatever is being tested. Now, set the selector switch on the meter to one of the ohms positions. When it is positioned here, you are getting a direct 1-to-1 resistance reading of ohms. When the switch is here, the reading is 10 times, and here, 100 times. When testing for resistance, you are looking for the specific resistance of a component or circuit. Therefore, you would probably set the selector on the RX1 setting, since most components and circuits have fairly low resistance. If you are testing for continuity, you are basically looking for a complete electrical circuit which would equal 0 ohms. Once the selection has been made, you must zero the scale. This pointer adjustment is used to zero the ohm scale. The zeroing adjustment is for the ohm scale only and must be repeated every time an ohm resistance reading is taken. To test for resistance or continuity, after selecting and zeroing the appropriate scale, apply the probes from the meter to the electrical terminals of the part that's being tested, like these terminals of this switch or these terminals of this receptacle. Then note the reading. It is essential that the probes make good contact with the terminals being tested. If it's possible to use alligator clips on the terminals being tested, use them. These clips usually make a firmer connection than the probes. These two scales are for measuring volts, AC and volts DC. To use the meter in these settings, power needs to be present. The selector switch can be used to affect all of these readings. When the switch is in this area, it is used for reading of volts AC. When taking a volt AC measurement and the value of the voltage to be measured is unknown, always start with the highest range of the meter and progressively go lower until an appropriate reading is obtained. In other words, if you're measuring the voltage at this electrical outlet, begin with the switch at the highest setting. By taking a measurement, you read 110 volts AC here. If the switch setting had been lower, you potentially could damage your meter. On the other side of the meter is the same switch settings for volts DC, direct current. Again, these settings function similarly to the volts AC settings. Ammeters are used to measure electrical current and work basically the same as the volt-ohm meter. Current measurements are taken off the hot wire in series with a circuit using an ammeter, whereas voltage is measured across the hot and neutral wires of a circuit. The ammeter has a set of jaws which are opened by pressing a lever on the handle. The jaws are then slipped over a wire, completing a loop around one wire in the circuit. This saves the need for disconnecting the wire first. If your ammeter has a selectable scale, always select the scale in advance of taking the reading, starting with the higher scale and moving down to avoid damage to the meter. You could use an ammeter to measure the current draw in the thermostat circuit in order to set the heat anticipator on a thermostat. You can measure the current draw anywhere in the thermostat circuit from the primary electrical source to the thermostat.
This section discussed basic electrical tools and how to use them. Also discussed was how to use basic electrical test equipment, such as a continuity tester, neon light tester, volt-ohm meter, and ammeter. Turn the videotape off now and complete Section E in your workbook.